Yes, you can proceed. Thank you.
Okay, good morning, everyone. My name is Rita Dantas, and I'm going to present you the work entitled Frequency Effect in Fatigue Behavior of a Structural Steel and Spring Steel. This work was developed by me and the colleagues that you can see here. First, I would like to show you the main topics of this presentation. I will start by introducing you the background and goals. Then I will characterize the two different materials that we study. Then I will move on describing the experimental campaign that we performed to assess the very high cycle fatigue region, and then explain you the frequency effect that we observed, and finally the conclusions and future works. Usually we have three different fatigue domains. We have the low cycle and high cycle fatigue region that is usually defined until the 10 millions of cycles, and we define our fatigue conventional limit here around the 10 millions of cycles. However, during the last decades we started to study the very high cycle fatigue region that is behind these conventional fatigue limits, and in this work our main goals are to study the very high cycle fatigue behavior of a structural steel and also a spring steel, and evaluate frequency effect in these two materials. So here you can see the characterization of these materials. We studied the S690 structural steel. This material was hot rolled, quenched and tempered, and we manufacture our specimen from a plate of 20 millimeters of thickness. And you can see here in figure 2 the microstructure, and that is tempered martensite, and the main, and in table 1 and 2, the main chemical composition, and main mechanical properties. Regarding the chemical composition, we have a low quantity of carbon steel, and we have ultimate strength of 800. On the other hand, spring steel specimens were manufactured from leaf springs. However, this material was also hot rolled, quenched and tempered, and the microstructure is very similar. However, in this material we have a percentage of carbon 4 times higher than we can observe in the structural steel, and regarding the material properties, we have ultimate strength higher than we can see in the structural steel, and also we have a less ductile material. Moving on to the gigacycle fatigue tests. We perform our campaign in ultrasonic testing system. This fatigue system is very different than a conventional one. We need to be more careful in design of our specimens, as I'm going to show you in the next slides. Besides that, we need to ensure that our specimen is not going to overheat due to the high frequency of testing. Therefore, we use a system to monitor the temperature during the fatigue test, and also we used a air cooling system to cool down our specimens. So here, I will not have many time to explain this, but here you can see a scheme of the procedure that we conducted to design our specimens. We need to ensure that our specimen is going to have one of the natural frequencies as 20 kilohertz. That is the frequency of testing of our machine. And in order to that, we need to calculate with considerable accuracy the elastic models of our materials and also the density. Therefore, we follow with analytical procedure that is already well described in the literature that you can see here on the left side, and after that we performed also a finite element modeling to verify the geometry that we defined for the structural steel and for the spring steel. Here you can see the geometries that we use it to test each of the materials that needs to be different because the properties of the materials are different, of course. So here you can see on the right side the numerical modeling and the stresses along the specimen, and as you can see, we have here a maximum stress at the middle section of our specimens. Another aspect that we need to be very careful is the surface quality. We need to polish our specimens after the machining process, and here you can see a figure of our surface quality before and after the polishing. What is more important, the results. Here we have the experimental data obtained in the ultrasonic fatigue machine for the spring steel and for the structural steel. The behavior of this material is kind of similar, however, we have some differences. In both of the materials, we have observed a large dispersion, that is a characteristic of this region, and the SN curves were almost horizontal. However, for the structural steel, we have a fatigue limit that is very close to the conventional fatigue limit. We observed that a few specimens failure after the 10 millions of cycles, and after that, all the specimens achieve infinite life. So we can say that we have a fatigue limit around 20 millions of cycles and of 520 megapascals. Regarding the crack initiation, usually in very high cycle fatigue, we can describe, it's very typical to find initiations, internal crack initiations. However, we only observe that in one single specimen, and most of the specimens failed on the surface. Regarding the spring steel, it was very similar. However, we have some specimens that failed after the 10 millions of cycles. In fact, we defined a fatigue limit around the 100 millions of cycles, and after that, all the specimens again achieved infinite life. Regarding the initiation, we again observed most of the cracks initiating at the surface. However, a few specimens achieve internal initiation. Then, in order to analyze the frequency effect, we perform experimental campaigns in two more fatigue testing device. One of them, it was in a resonance machine that allow us to test at a frequency of 150 hertz, and for the spring steel, besides this machine, we also used a conventional fatigue rotating bending, which allow us to study at 23 hertz. So you can see here the results that we obtained for the different experimental campaigns. For the spring steel, we were able to study 3 different frequencies of testing, and as you can see, the main difference is between this 150 hertz and the 20 kilohertz. So the frequency effect is significant in ultrasonic frequencies of testing, and besides that, one thing that we can see in both of materials is that the frequency effect increases with the number of cycles. Here in this region, the data is in fact very close and they converge for the same value. However, in the fatigue limit, we have a difference of around 8 megapascal and 90 megapascal. This shows us that we need to be very careful when we are testing this kind of frequencies, and probably we will need to apply an analytical formulation to consider this frequency effect. We can see this effect described in the literature for other authors, and it will depend a lot on the material. As you can see here, we have 2 different plots from different authors with different frequency effects depending on the material. And again, you can see that for the ultrasonic frequency of testing, we have a more severe frequency effect. So, in conclusion, we can see that for this material, for the spring steel and for the structural steel, if we conduct some experimental campaign in ultrasonic fatigue testing, we need to take in consider the frequency effect, and probably in the future we'll have to consider some from analytical or other nature formulation to include this frequency effect to be able to use this experimental data to design some structures or something like that, because without that we were not able to reproduce the real behavior of the material. So it's that. Thank you for your attention. I hope to be able to explain you everything in 20 minutes. Thank you.